Yes, it's both a great pleasure and a great honor to be here on this occasion. Most of the talks so far have been somewhat retrospective, and I'm hoping to continue looking toward the future. I was hanging around the observatory yesterday, meeting old friends and dodging ghosts, and I was reminded of the time when I was just finishing my undergraduate work at Harvard, and my advisor at the time, Leo Goldberg, gave me some excellent advice. Actually, two pieces of excellent advice. The first was that as I was about to start my PhD studies, that I really should go meet Alex Dalgarno and ask him to give me a project to work on. And I gladly followed that advice, and I continue to be grateful that I did. The second piece of advice that Leo gave me was that you really should try to become a master of one particular topic and develop that. I willfully ignored that advice and have dabbled in all sorts of things since and have had a great time. But I do appreciate it was good advice anyway. It's, I think, comforting to know that there continue to be young people popping up and entering this field of atomic and molecular astrophysics. And so this is just another one of these photographs, but the very tall fellow here is my most recent PhD student, Akim Tapa, who's here in the audience and is now a postdoc at the Center for Astrophysics. And so I think that there continues to be hope for the future. Whoops, the wrong direction, sorry. But I wanted to look forward a bit. And in particular, what I wanted to talk about were some of the themes that Alex has set for the rest of us through much of his work that have still left open-ended problems, and to look at some of the problems that are still interesting me and at times troubling my sleep. I thought I would quote the famous American philosopher and baseball player Satchel Paige, "Don't look back, something might be gaining on you," and that's the reason for continuing to look into the future. In thinking about this musical analogy of themes and variations, there are three themes that I thought I would choose for this talk. One is this embarrassing question that keeps coming back, whether astrochemistry actually makes testable predictions, or whether we're constantly fooling ourselves with wishful thinking and self-delusion about whether or not our predictions are actually accidental when they agree with observations. I think the answer is sometimes, and I'll mention one specific example of the chemistry of fluorine in the interstellar medium. We've also heard a little bit already about primordial chemistry, and I'd like to say a few words about whether some aspects of that might be observable, testable directly by observation. And then there are some subjects that Alex has worked on quite a lot in other contexts, especially the speed distributions of molecules and atoms in gases, with obvious applications to planetary atmospheres and escape from atmospheres. But I think that there are also some very interesting applications to interstellar matter and other very dilute gas in space, where these issues have not been properly addressed yet. You've actually seen this quotation and a reference to this review article already this morning. And as I said, there are many instances where some of the agreement between theory and observation has probably been illusory and accidental. And again, we learn from our failures. That's certainly been my usual way of working because my failures are so abundant. In any case, the theme set here, let's look at one case where I think there are some testable predictions. That's the very interesting interstellar chemistry of fluorine. And a very interesting theme was set and developed by Ju, Krems, and Dalgarno and Balakrishnan in 2002, where they investigated in detail the low-temperature behavior of this very important chemical reaction of atomic fluorine with H2 that forms HF, and demonstrated that it remains rapid for ground-level fluorine, that is in the lower fine structure level of the ground term. It remains rapid at low temperature and thus strengthened the earlier suggestion by Neufeld and collaborators that gaseous fluorine in molecular clouds should go mainly into hydrogen fluoride. A variation on this that was subsequently developed in another paper by Neufeld et al. In 2005 was the prediction that CF plus should also be an abundant byproduct. This is because the reaction of carbon plus with HF is rapid, and carbon plus is one of the more abundant ions in interstellar molecular clouds, especially those that are exposed to ultraviolet starlight. And then finally, this prediction, a quantitative prediction, was confirmed by the observation of CF plus in the Orion bar photon-dominated region. And here are the spectra to prove it. 3 different rotational transitions of CF plus observed in the same place through the use of 2 different telescopes. And this gives me an opportunity to show a beautiful picture of a beautiful telescope. This is the 12-meter Atacama Pathfinder experiment situated in the high desert in northern Chile. And I wanted to point this out because Sweden does have a 23% share as one of the significant partners in this telescope. And I think it's going to be contributing quite a lot more observationally to the study of astrochemistry. It's possible to make other predictions about other ways of looking for fluorine compounds, in addition to looking for the pure rotational lines of HF in the far infrared and submillimeter region. It's possible to look for the infrared vibration rotation spectrum in absorption toward infrared sources. I'm afraid the lines may be a little bit thin in this graph, but there is a blue curve, which is the calculated interstellar absorption spectrum. And the red curve shows the atmospheric transmission in that region. It turns out this is one of these very difficult observations to make from the ground, and basically impossible from space because those who design space projects like the JWST, the James Webb Space Telescope, don't appreciate the importance of high-resolution spectroscopy, and therefore there will be no high-resolution spectrograph on the JWST. Okay, on to another theme, the primordial chemistry in the early universe. You've already seen brief introductions to this, and so I won't go into much of that. But this, as Alex, together with Stephen Lepp and Philip Stansel and others have shown, there's a surprisingly rich chemistry, despite the fact that there are very few raw materials available before the first generation of stars has a chance to pollute the universe with heavier elements. But there remains this question of whether this is the ideal problem for the theorist, totally beyond experimental test, or whether there might be some possible observational consequences of the primordial chemistry. In one slide, this is the history of the early universe, the thermal history, showing that with increasing redshift, which is taken as an observational surrogate for expansion age of the universe, that is, redshift measures the look back into the distant past of the universe. Zero redshift is the present time, and higher redshift is the very distant past. In the very distant past, the temperature of the matter, T sub m, and the temperature of the radiation were identical, strongly coupled to each other by electron scattering of photons. But at some epoch around a redshift of about 1,000, the universe started to become transparent to the radiation. The matter and radiation decoupled from each other thermally, and the temperatures diverged. Also, at about the same epoch, the universe was recombining, becoming almost fully neutral from a previous state of complete ionization. And this shows the variation with redshift of the number densities of the principal hydrogen species, neutral atomic hydrogen molecules, and also the rare but very important H-, which goes through two peaks in abundance with cosmic time in the past. The interesting thing about H-, as Philip pointed out, is that it absorbs relatively long wavelength radiation compared with other forms of hydrogen. And this means there is a possibility that H- might be detectable through its absorption, its continuous absorption. And that was the point of this little calculation, to estimate the optical depth of H- integrated through the universe back to the point at which the cosmic background radiation was formed, to see whether possibly the H- might produce a detectable spectroscopic distortion of the cosmic background radiation. The red curve in this graph shows a Planck function that is the spectrum of the cosmic background radiation, which has remained to an excellent approximation a black body. That is something that has been confirmed by observation to a high degree of accuracy. The red curve, as I said, shows the spectrum of the cosmic background radiation. The blue curve shows the optical depth, dimensionless optical depth of H- as a function of frequency divided by the speed of light, so in spectroscopist units of centimeters to the -1. And the possibility of a very small distortion at the higher frequencies, very far away from the peak of the background radiation spectrum. But, and as I said, there has been a direct observational limit on deviations from a perfect blackbody spectrum in the cosmic background radiation provided by the COBE satellite. This limit was published in 2002, and the bar, the solid bar in this diagram, indicates the current upper limit. A simple estimate of the spectral distortion by H-, the primordial H-, suggests that within a factor of 8 or so, there might be a distortion relatively close to the peak of the cosmic background radiation. And already in this 2002 paper by Fixen and Mather, there was a section in the article pointing out that in the future, the sensitivity to the blackbody spectrum could be improved by factors of up to 100 with existing technology. So seeing a distortion of this size should be possible in the future. However, this may be one of the cases where I will have to learn from my mistakes. I'm not certain yet, but there's a recent preprint that has repeated that calculation in a little bit more detail and disagrees about the magnitude of the H- distortion. probably the origin of the disagreement has to do with the treatment of the inverse processes, the contribution of the free bound emission that would fill in the absorption, and also on the extent of departures from equilibrium at redshifts between 1,000 and 100. Anyway, stay tuned for more on that in the future. I won't say more about the H- since Philip already covered that in some detail. Now, one other thing that's been interesting me is to explore the variations on these very interesting themes having to do with discrete energy loss when electrons enter gases of various mixtures, which has obvious applications for the heating and ionization by X-rays and by cosmic rays in the interstellar medium and elsewhere. And then some related issues about the collisional approach to thermal equilibrium. There are several questions that come up. Are the speed distributions, especially in the interstellar medium where the density is very low, are the speed distributions truly Maxwellian? If we follow the usual textbooks on the interstellar medium, then we've been assured that to good approximations they really are. Actually, if one looks very closely at Lyman Spitzer's classic textbook, or textbooks on the physics of the interstellar medium, there are a few paragraphs that justify the Maxwellian approximation and then say that there may be some departures of the order of a few parts in 10,000 or something like that in the electron speed distributions. And then basically nothing much has been done to follow up on that. It turns out that such small fractional deviations in the high energy end could have some interesting consequences. Does it matter if there are small deviations? Well, yes, it might. I'll say a few more words in detail as we go along. And it also turns out that even though all of the processes that affect the calculation of ionization efficiencies and dissociation efficiencies in molecular gases and hydrogen-helium mixtures, even when all of these processes have been nicely assembled and organized, in fact, not enough has been done to incorporate all of that information into the most recent astrochemical models of interstellar chemistry, so that one could actually start with a more modern and more realistic primary input spectrum of cosmic ray nuclei and also of primary cosmic ray electrons, which are also going to be important, and to propagate through that through the structure of a molecular cloud in which the fractions of atomic and molecular hydrogen vary with distance. So that still needs to be done. And of course, there remains this long-standing mystery of why there is interstellar CH+, why it's so widespread and so abundant. It's one of the more abundant interstellar molecules. 4 times 10 to the minus 8 is a fraction of the H2 and is widely distributed in space. And I think that even though some very interesting progress has been made in terms of accounting for the abundance of CH+, in terms of the dissipation of turbulence in interstellar clouds, that it's not fully explained yet. Part of the reason I say that is that while turbulence is an attractive way of adding super thermal energy to the low temperature interstellar medium, turbulence per se is a hydrodynamical phenomenon, and the fluid mechanical descriptions of turbulence still do not tell you explicitly what happens at the microscopic scale where the chemistry occurs, where the actual reactions take place. And so I think that an interesting program for research is to try to understand better what happens at the truly microscopic level. at the bottom of the turbulent cascade, if indeed that is what is responsible. One way of describing the interaction of all of some of these things is to consider basically what's happening in a dilute interstellar cloud where the kinetic temperature is somewhat less than 100 Kelvin. The observed fractional ionization of atomic carbon, for example, corresponds to an ionization temperature of 3,000 Kelvin or so, if it were in equilibrium. Well, in fact, it's in a photoionization equilibrium, and this is roughly characteristic of the brightness temperature of the ultraviolet starlight on average in an average place far away from the nearest hot star. The fine structure level populations in carbon ions and carbon atoms are often subthermal and therefore characterized by an excitation temperature which is different from any of the others, and so on and so forth. So already we have a proliferation of temperatures, different meanings of temperature. Again, the question of whether atomic and ionic and electron motions are thermalized in any sense. It's also interesting to keep in mind the very unusual physical scales that we need to describe these things in dilute matter in space. For example, an interstellar cloud might have a size of the order of 10 to the 16th meters or more. The mean free path for a thermal hydrogen molecule of the order of 3 times 10 to the 9th meters, already 1/100th of an astronomical unit. A thermal electron in one of these low temperature interstellar clouds would have a mean free path for momentum transfer collisions with hydrogen of the order of a few tenths of an astronomical unit. And a photoelectron produced by starlight photoionization or the photoelectric ejection from dust particles or large molecules will have a mean free path of the order of tenths of astronomical units. For electron-hydrogen collisions, somewhat larger for Coulomb interactions. Okay, so I think there's quite a lot, much more to explore in terms of what happens as a result of the photoelectric heating, the photoelectric effect, because the dominant photoelectrons, the initial photoelectrons in the interstellar medium come off with 3.5 electron volts or so, something of that order, a few electron volts. And they're born in a region where the mean thermal energy at temperatures less than 100 Kelvin, the mean thermal energy is millivolts instead. So a lot is happening to those photoelectrons, and it's of some interest to follow in more detail what's going on. It is vaguely possible, I think, that in fact it's more the result of the what happens to the photoelectrons and how they interact with the neutrals and the positive ions that may drive the superthermal chemistry that results in CH+, rather than the turbulence. And part of the reason for saying this is that it can be argued quantitatively that the photoelectric heating is of the order of magnitude greater than any heating effect, total energetic effect of the dissipation of turbulence. I'm rushing through these slides just so that we won't delay lunch too much. But to summarize some of the interesting aspects of these issues that I think still remain to be looked at, let's remember that these photon-dominated regions of neutral clouds are weakly ionized plasmas. At the energies of the initial photoelectrons, it's the elastic collisions with hydrogen atoms and molecules that are much more probable than collisions with other electrons. So the electrons do not thermalize by interactions with other electrons in such weakly ionized plasmas. And even though not very much is transferred from the light electrons to the heavier hydrogens, a little bit of energy is. There will be some effects on the hydrogen as the electrons lose their energies. The other thing to remember is that even though the magnetic field strengths are weak, of the order of 10 microgauss or less in the average interstellar medium, at these low densities, this is quite enough to be very important for the electrons and the positive ions. And so both the ion and electron distributions, velocity distributions, are likely to be anisotropic, and moreover, there may be some observable consequences ultimately in the speed distributions of the ions. Are there chemical consequences? Well, that still remains to be worked out. This is just to show the comparative magnitudes of the momentum transfer cross sections for different kinds of processes. Well, that has used up much of my time. I want to say once again that the seeds for all of these, I think, imperfectly solved problems have been planted by the work that Alex and his students and collaborators have done over the years. And there's remains quite a lot to be done to keep us all busy for quite some time into the future. And so I'll close with another quotation from Satchel Paige, that age is a question of mind over matter. If you don't mind, it doesn't matter. Thank you very much.
Are there questions or comments? Eric?
Another area which non-thermal distributions matter, and that is deuterium fraction. Yes, it's also worried me for some time that our theories of deuterium fractionation are strongly based on thermal distributions.
Yes. Yes, this is a problem in several different ways. One is, as you say, that the not just the deuterium fractionation, but essentially all of the gas phase rates that are commonly used presume thermal speed distributions for the reactants. And those are applied in places where, well, possibly there may be some non-thermal excesses. Yeah.
It's the slightly endothermic ones that are the most sensitive.
But especially for the slightly endothermic processes, then a small excess in the speed distribution might play a big role. There's another aspect of the deuterium fractionation, and that is that the most important processes may be very sensitive to the rotational population distributions of the reactants, which couple to the population distributions of the products as well. And those are certainly going to be non-thermal, the population distributions, which means that the excitation problem and the chemical problem really should be solved simultaneously. So there has been some work along those lines, but I think a lot more to be done to perfect the calculations.
Yeah, well, let's thank John Black and also Bill Klemper for chairing the session.